Hello YouTubers, welcome to Leicester Electronics. I'm your host, Lester Wyatt. Right, this is my first ever video tutorial blog on electronics. So I feel it's a good time for me now just to give a quick introduction and tell you about myself. Yes, I live in Oxford, which is a city in the UK. I'm a professional electrician and an amateur electronics enthusiast. Right, well, I'm guessing if you're watching me, you're just starting out in this this subject, electronics. So where do you start? I do know that you got to walk before you can run. So the basis of this tutorial is Ohm's Law, talking about voltage, current and resistance. It's going to be explained with a simple circuit. It's just going to be a resistor and a power supply, and that's all we're going to need for this tutorial. So if you're playing along at home, there'll be a few things that you need. You're going to need a pen and paper, a calculator. It doesn't have to be a scientific one, but the one I'm using, it's a very good calculator. It's a Casio FX83 GT. Like I said, for this tutorial anyway, you're only going to need a basic one, but for following ones it will get more advanced and you will need a scientific calculator. You're going to need a breadboard, yeah, and that's not something that you cut bread on for all you beginners out there. It's one of these. I don't want to explain the pin out, and there's plenty of things, documentation on YouTube actually if you want to know, but they're pretty straightforward. I'm assuming that you know about them anyway. And we need 3 resistors. I'm going to assume again that you know your resistor colour codes. Anyway, we're going to need a 1k resistor, 5k resistor and a 10k resistor. You're going to need a 9 volt battery and some jumper wires, and you're going to need a multimeter. I'm going to be using the Fluke 87V, but you don't need to use anything as advanced as that. You can use any cheap multimeter, it still works for what we're doing today anyway. Excellent. So, shall we walk on over to the bench, and I'll walk you through a few things. So follow along, play along at home, you might enjoy it. So here we are at the bench. Right, before we touch upon Ohm's Law, we need to get a little understanding of the variables we're going to be working with, i.e. voltage, current, resistance. What are they? It's a good question. They are simply units of measurement that we use in electronics in order for us to do our calculations. Voltage has a unit value of a volt. Current has a unit value as an amp. And an amp is a number of electrons that pass a point in 1 second, and that would be there or thereabouts 6 times 10 to the power of 18 electrons every second, which is a very large number. Don't ask me to write it down, Google it if you're that interested. Resistance has a unit value as an ohm. Right, people often ask me to explain what voltage is, what current is, and what resistance is, and what effect it has on a circuit. I've got a nice little analogy, you've probably heard of it before, that I like to use, and it explains it very well. Right, let's have a look. It is the tap analogy. There we go. Right. Everyone's got a basic understanding of how taps work, where we undo that stupid little thing on top and you get more water. And that's basically how our circuit's going to work. Right, let's have a look. Let's change a few things. Right, the pressure in our pipes in order to push the water out, we're going to call that our voltage. Our water, we're going to call our current, our electrons, current, and our little valve here in our tap, you know, that we screw and unscrew, we're going to call our resistance. Now, let's imagine that we got 6 volts of pressure in our pipes, and we have a certain resistance. I'm just going to put anything down here. Let's just say we got 1k of resistance, and with this little resistance we have a certain amount of current coming through here. I'm not going to do any calculations now, so don't beat me down if this is just off the top of my head. Let's just say, actually let's add a little glass here, and we'll call this 1 amp. This can be our amp glass, yeah? Before I go any further, you know, I'm not going to have an amp flowing out of here with these values I've put in. We're just using this analogy and just use your imagination. So here we go. So we've got 6 volts of pressure. Let's add it. I don't want to complicate it. Let's add a little stopwatch. Everyone's familiar with a stopwatch. It ticks every second. So back to where we was before. So we've got our 6 volts of pressure, and we've got our resistance, and now we've got a current flow that's filling up our amp glass. And as it is, this glass is filling up every second. So it's filling up, we're emptying it, it's filling up and we're emptying it every second. So that gives us 1 amp. Right, now let's change our voltage to 9 volts. We keep our resistance. Right, so we start off again, start our stopwatch. This time the amp glass is overflowing before the second is reached. So this means that we must have over 1 amp of current flow. Okay, so this time we keep our voltage constant, 9 volts. And what we're going to do now, we're going to screw up our little valve so we got more resistance. Let's change our resistance now to, say, 2k. So start our stopwatch. This time it's flowing, but every second is not quite filling up. It's reaching probably 2/3 of the way. And as it is, you know, it's probably ticking, has to tick 2 seconds before it's filled up. So that's that one. What we're going to do now, we'll change our voltage. We keep it at 2k, and we change our voltage now to 12 volts. Our resistance is kept at 2k, 2000 ohms. We start our stopwatch again, and as it is this time, we are getting 1 amp of current flow every second. We're filling up our glass and emptying it. And the relationship we're seeing here, that is, if we keep our voltage constant and we change our resistance, we can control the flow, the current flow. Or if we keep our resistance constant, change our voltage, we can again control the rate of current flow. And that's exactly what happens, that's going to happen in our circuit or in any electrical circuit. So if you take a look at that for a moment and get a bit of an understanding of what I said, and once you think you've grasped that, we'll move on to Ohm's Law, where we'll do a little bit of theory on it, where we'll draw out some simple circuits and put in a few arguments and use Ohm's Law to calculate the values that we require, and then we'll put our theory into practice on the breadboard. So let's go. Right then folks, now that we've got an understanding of the variables we're going to be working with, let's take a look at Ohm's law, i.e. the Ohm's triangle. You've probably heard of it before, most folks in this game have. Let's take a look, more in-depth look. So what this enables us to do is to find a variable that we're looking for. So for instance, say we know what our current is and we know our resistance, but we need to know the voltage. So what we do, we cover up the variable that we need, and we're left with simple math to find the variable. I times R, so we times the current by the resistance, and that would give us the voltage in the circuit. And again with the current, we need to find the current, so we cover up that variable and we divide V into R, and that will give us our current. And the same with resistance. Cover up R, again V divided by I, voltage divided by the current, and that gives us the resistance. So now let's look at a few example circuits drawn out with arguments in them. We need to find the variables. Let's take a look. The ones I prepared earlier, just like Blue Peter. Here we go. Hope you can see that. That's fine. Let's get them all in shot. Right. So here's our simple circuit here. Circuit 1. We have a 9 volt supply and we need 1.9 milliamps running through our load, our circuit. So what resistor will we need for that? So what I'll do, so looking at Ohm's triangle, we need to find R. So R equals V over I. So R equals V over I. We know what our voltage is, 9, and we know what our current is, 1.9 milliamps. So R equals V, which is 9 volts, and 1.9 milliamps. Right, in this example I'm going to be using a scientific calculator, and I'm going to be using scientific notation. For those of you that have got just the basic normal calculator, I'll show you how to punch that in. That's if you don't know anyway. Here we go, sorry about that. 9 volts over 1.9 times 10 to the power of minus 3, because it's milliamps. And what you need to put in there, if you've got a basic calculator, it's a 0.0019. So R equals, I'll just plug that in my calculator, just catch it, hold on. So I'm going to see if I can get it right. I've got fluorescent light fittings in here and it's annoying this shot, I think. So 9 volts divided into 1.9 times 10 to the power of minus 3 equals 4,736, and we're around that 4,737. So that's 4,737. 37. So that gives us our resistor that we need in that circuit. So what we do, we take that down to the closest resistor that we got, and that'd be a 4.7k. 4.7k. Now let's look at circuit 2. Right, we've got 1.5 milliamps running through our circuit, and we have a 1k resistor. What voltage are we going to have running through that circuit? Ohm's Law will tell us. Let's take a look. So, let's look at Ohm's Law. So V I times R will give us V. So here we go. Wound it in the way, fine, yeah. So V equals I times R. So let's have a look. We know that I is 1.5, again 1.5 times 10 to the power of minus 3 times 1000. So V equals, let's get the calculator again, so 1.5 times 10 to the power of minus 3 times 1000 equals 1.5 volts. So that we found, so for 1.5 milliamps with a 1k resistor, you're going to have 1.5 volts. Now let's look at circuit 3. Let's move that up a bit, there you go. I'm a bit of an amateur with video photography, so you're just going to have to bear with me. So let's have a look at circuit 3. We have 9 volts running through the circuit with a 10k resistor, that's a 10,000 ohm resistor. What current do we have running through the circuit? Let's take a look at the Ohms triangle again. So, cover I equals V over R, V divided into R. Let's write this down. So I equals V over resistance R. I equals V, 9 volts, over R, it's 10k. It was actually easier to put that down in normal notation than scientific, so right, so V over 1k, so I equals, let's get the calculator, (9 volts over 10,000, 10k, equals, that is actually 0.9 milliamps. I equals 0.9 MA. So, excuse me, so now that we've done our theory, I think it's time now to do some fun stuff, do a bit of practical on the breadboard. And we're, oh yeah, sorry, before we go any further, I'll just want you to take a look at this. A lot of you probably know, but just for you beginners out there, if you're not quite sure, we're going to be using our multimeter in circuit, and I just want to explain a few things. When we come to measuring the current, we measure current in series with a circuit. So if you can take a look at that, this drawing here. So you've got your multimeter set up on the milliamp scale, usually the lowest scale on the cheap multimeters is usually the 200 milliamp setting, and the other lead in the COM port, and you take your current reading in series just like that. And when you're measuring voltage, you always measure it across the load. And again, once you've set your multimeter up, usually the COM, usually the black lead in COM, and V, your red lead. And on your voltage setting, your DC voltage setting, and again the lowest setting on that, which is usually, depending on what multimeter you got, it can go down to 200 millivolts. Yeah, so you always measure that across the load, like so. So your current in series with the circuit, and your voltage, across the load. So now that we've done that, we're set up our breadboard, and we're to see if our theory matches our practice. I'm sure it will. So here we are at the breadboard. Everything's set up. I've got our first argument, which was circuit 1, which worked out as we needed a 4.7k resistor to get 1.9 milliamps at 9 volts. I am using a regulated power supply, so if you are using just your normal 9 volt battery, it may be a good idea just to take a voltage reading of it, because sometimes it does vary quite a bit, and if it does vary quite a large amount, you may need to do the calculation again. Anyway, my breadboard's set up, ready to go, with a 4.7k resistor at 9 volts. So, right, let's see if I can get everything in view. With the Fluke 87V set up in current mode, milliamp scale, my actual multimeter here, it's auto ranging, so you're going to make sure that yours is set on milliamps. So here we go, the moment of truth. Let's set my voltage on. 9 volt, actually it's 8.95, and look at that, just as we predicted it with our calculations, 1.9 milliamps. Excellent, I'm happy with that, and I hope the same is up with you guys. Excellent, let's look at circuit 2, and that was, we had 1.5 milliamps with a 1k resistor. So for you guys, you can just get yourself a normal AA battery. They're usually 1.5 volts. Again, they may vary, so you will have to measure them on your voltage scale like I showed you. So right, I'll plug in that value now. So what I need to do is put that there, sorry, take the 4.7k resistor out and our 1k resistor. Before I put that in, I'm going to lower my voltage to 1.5 volts DC, because that's what Ohm's law says, and it is the law, remember, so it's got to be right. So it's dialing 1.5, what we got? We're just over. We've got our 1k resistor. We put that in circuit, and what we got? Look at that, 1.53 milliamps. Again, it's agreed with our calculations. Ohm's law is never wrong. Remember that. So, circuit 3. Our argument was that we had a 9 volt supply with a 10k resistor. And with that 10k resistor in, we should expect 0.9 milliamps. So I'll pull the 1k resistor out. Find our 10k. Obviously I'm going to have to increase my voltage to 9 volts, and you guys can use your 9 volt battery. Let's have a look. 4, 5, 6, 7, 8, 8, 6, 7, 8, 9. That's close enough for me. Let's have a look. Let's put our 10k resistor in the circuit. Look at that. 0.91 milliamps. That's close enough for me. So there you go. These it's agreed with Ohm's law. With our calculations and our practical experiment, it's agreed bang on actually. Very pleased with that. So, why are we doing all this? Well, what use does that circuit have there? You're probably asking yourselves. At the moment, it's no use whatsoever. But for a little bonus, I'm going to give you a little sneak peek preview of what we got to come. This is it's just going to be all we're going to be doing is adding an LED in circuit. That's a light emitting diode. The moral to this, all this stuff that we've done today, was that any load, even an LED, requires a certain amount of current to run, and if the current's too high, the LED will blow up, and if it's too low, it won't even light up. So in order for an LED to light up beautifully, if you like, it has to have a certain amount of current running through it, and this is what this is all about. So if you can find yourself an LED, a red one preferably, because that's what I'm going to be using, that's where we're going to do our calculations, it'd be excellent. So get yourself an LED, a red one, and come back. So there you have it, the LED, light emitting diode. Hopefully you've got yours now. Well, you'll probably notice there's two legs on the LED, and one of them's longer than the other. We would call that the anode. And the smaller leg we'd call the cathode. The anode needs to be more positive than the cathode. So the longer leg goes on the positive supply, and the smaller leg goes more negative, on the negative side of the supply. So let's put this LED in circuit without a current limiting resistor. See what happens. So I've got my 9 volts on my power supply, and we're just going to pop it in. See what happens. There she is, bless her, all on her own, in a 9 volt supply, without her friend the resistor. Let's have a look. I'm just going to put the supply on 9 volts and see how she glows. Oh, there she goes. Oh dear. She lasted for about 2 seconds. So what we need to do, we need to use Ohm's law and calculate the current limiting resistor that we're going to need typically a red LED will light up nicely with around 7 milliamps running through it. So let's go back to the drawing board and do some calculations and see if we can't design a little circuit where she will happily glow forevermore. So I've drawn our new circuit, and all we need to do now is use Ohm's law and calculate the resistor needed so we don't blow the next one up. So we've determined that we need 7 milliamps running through this circuit for the LED to be happy. So let's have a look. Let's have a look at Ohm's law again. There's a slight little difference to this calculation, but it's very simple. Typical LEDs, especially the red ones that we're using today, there's a 2 volt drop across them. That's all you need to know at the moment, just a 2 volt drop across them. So let's have a look at our Ohm's law calculation. So we need to find R. So our new formula is going to look like this. Vs take VL. Stick with me, looks worse than what it is. Vs is our supply voltage, which is 9 volts. And VL is the voltage drop across the red LED, which is 2 volts, divided by I, which is 7 milliamps. So we rewrite this. R equals 9 take 2 divided into 7 milliamps. That's 7 times 10 to the power minus 3 equals, let's do a quick calculation. It's probably not relevant me doing this. Actually I'll do it and then I'll show you the answer. So 9 take 2 volts divided 7 times 10 to the power minus 3 equals 1000. And it just so happens that I have a 1k resistor. How about that? So we put that in. R equals 1k. So R equals 1k. And it just so happens I've built up the circuit and I've put the 1k resistor in. There she is. Doesn't she look happy there with her resistor friend? Zoom in a bit. Actually, we'll see if we can get the multimeter in with it. Right, there you go. That'll do. Right, you're going to come on. You don't want AC on, want milliamp. There you go. 9 volts come in. Let's review that. 9. That'll do, just close enough. 8.97. Right. There we go. That's a total fail because have I just done a schoolboy error? Yes, I have. I've got the LED in back to front. Silly boy. Let's put it back in the right way. There you go. And look at that. 6.92 milliamps. I think that's quite close to 7 milliamps, don't you? So I'm happy with that. And most importantly, so's our little LED. I don't know if you can see it. I think the light's a bit terrible in here, but yeah, I think it's to do with the infrared filter that I got on the camera. Anyway, she's merrily shining along, and ta-da, 6.92 milliamps. I'm very pleased with that, and I hope you lot are too. Well, I hope you enjoyed my first ever video tutorial on Ohm's Law. I hope you gained some valuable information out of it. Anyway, if you've got any comments, leave them below. And if you enjoyed this video, give it a massive thumbs up. Right, I'm tired now, so I think what I'm going to do, I'm going to go and have myself a shower, and then I'm going to go to the pub. Catch